So in this video, we're going to look at ordinary least squares in that we're going to solve for a quadratic, a cubic, and a linear equation in the plane. So what I'm going to assume here, as you can see in the introduction, I'm going to assume that you are familiar with vector operations, adding a vector, subtracting vectors, multiplying a vector by a constant, etc. Matrix operations, including the transverse of a matrix, the inverse of a matrix, and then matrix vector multiplication. Very specifically, the column space of a matrix, the concept of linear independence of those column vectors inside of a matrix, and then the projection of a vector onto the column space of a matrix. At least if you're familiar with these things, I'm going to explain some of them in an intuitive sense so that you understand the use of least squares when we're trying to approximate a solution. So the packages that we're going to use in this Jupyter notebook, or then a Google Colab notebook, is I'm going to import warnings and then just set the filter warnings to ignore. So I'm going to set the %config magic there just because this is a retina display and I just want those images to be nice and crisp. And then from a matplotlib, we're going to import that pyplot module as PLT. And then I'm just going to set a font because I'm going to use a specific theme when I do my plotting. Then I'm also going to import numpy using the namespace abbreviation np as usual. And then from the symbolic Python package, sympy, we're going to import the matrix function that's an uppercase M. So here's our example problem. Let's set up this problem. We have a two-space, so Cartesian plane, x and y coordinates. And we have these 3 points, 1.5, 1, 2, 5, and -1, -2. And as you can see here, we have this this picture here of the problem. And that's the theme I'm using, XKCD, very famous. And, it's just a bit of whimsy as far as our plotting is concerned. And what we want, first of all, we're going to find this quadratic approximation through the points. So remember, a quadratic function, that's a second order polynomial to go through these points. Polynomials such as y equals x squared, for instance, that it goes through those 3 points. Now, it's also got to go through the origin there. We're not going to set any kind of y-intercept. And that's going to be very difficult. There's not going to be, we'll see that there is no quadratic polynomial that is going to go through those points. So let's start then with this quadratic approximation of the solution. And I show you here y equals a sub 1x plus a sub 2x squared. That would be a polynomial that goes through the origin. In other words, there's no y-intercept. We're not adding some constant to that. But I have these two coefficients, a sub 1 and a sub 2. So for instance, 3 equals -4x plus 2x squared. Now that is a polynomial and it might go through those points. We need to solve for those coefficients. And if you're using this in some kind of application, for instance, linear regression, we usually use the coefficients beta, and we usually use a beta hat just to denote that this is going to be an approximation. For instance, we have a sample taken from a population and we're just estimating those population parameters by the sample values that we're going to calculate. So we use beta with a hat on, and for a sub 1, that specific coefficient, we can use beta sub 0, and for a sub 2, we can use beta sub 1. So in the end, we're going to have this equation. And we've got to solve for those beta values. So y is going to be approximately equal to beta sub 0 times x plus beta sub 1 x squared. So if we look at the 3 points there in equation 2, remember the first point was 1.5, 1. So 1.5 was my x value. So we can see my first coefficient times 1.5 plus my second coefficient times 1.5 squared. And that should give me 1. And the second point was 2, 5, and the third point was -1, 2. So you see the y approximately equal 2. And if I have these values, beta sub 0 and beta sub 1, it's going to approximately equal those 3 y values given the 3 x values. So if we write this in vector notation and then using a matrix, so we put all the y values in a vector, and we're saying that vector is approximately equal to, now this is a constant times a matrix, a constant times a column vector, I should say, beta sub 0 times my vector of x values plus beta sub 1 times each value squared. So if I write this with a matrix, I'm going to say y is approximately equal to this vector and this column vector all in a matrix. So that's what we have here on line 3. This x here representing a column vector, and x squared, my second column vector, times beta hat, and that's a vector with the 2 values. And you can see when I multiply this matrix by this vector, I'm going to approximately get this 152. And that's what we write very neatly right at the bottom. So y, my vector y, is going to be approximately equal to some matrix times my vector of unknowns. And what I need to solve for is those vector of unknowns. That is what I really have to solve for. And that's going to be a slight problem because we see that approximation, and we'll see shortly why this is just an approximation. So just want you just to realize one thing. We're going from our points, which is in 2 space, we're going to 3 space here. Those two things don't have anything to do with each other. Those points that we had was in 2 space, but I'm taking all the x values and y values, setting up a quadratic, and now we are in 3 space because we had the 3 points. So this is what we're trying to solve for, and I'm going to show you just over here on this tab. Let's go there. It's just a little Google drawing of what's going on with this least squares. So if you think about our 2, now this is not a representation of our actual problem. This is just some schematic of our problem. So our column vectors, we had 2 column vectors in our matrix A. And imagine these are these 2 blue vectors there. Now they're in 3 space. We can see the x coordinate, the y coordinate, and the z coordinate. And because we only have 2 of them, if they're linearly independent, which we've shown here, they're only going to span a subspace of 3 space here. They're only going to span this plane through the origin. So if they're linearly independent, they're going to span, so a linear addition of all of these. So if I sum constant multiple times vector A plus some constant multiple of vector, the second column vector, I can land up anywhere in this plane, but I can't get out of this plane. And my problem is y, as you can see orange right up here, that is not in the plane. So my vector y is not in the column space of my matrix A, and that's a problem. Fortunately, we can find this projection of y onto the column space. And we do that so that this perpendicular to this plane, there is a point on this plane that goes out to y so that this distance is the shortest possible. If this is perpendicular projection down onto the plane. And now you can see we've decomposed y into y parallel, because I'm just using y parallel there because it's parallel to the plane, and then y perpendicular because this perpendicular component, that is going to be orthogonal to my plane. And that makes it very interesting because any vector that I've got in the plane with a dot product with this y perpendicular should give me 0. They are orthogonal. So any vector in this column, dot product, and you've got to remember that becomes very important. What we can solve for, if we can't solve for y, is at least we can solve for y parallel, because y parallel is in the column space of my matrix A. Some linear combination, some linear addition of these 2 column vectors, these blue ones, will give me y parallel. That's absolutely possible. So I can at least solve for that if I cannot solve for y. Seeing, as you can clearly see there, y is not in the column space of A. So what we have here at the bottom is I have my matrix A consisting of these 2 column vectors multiplied by these coefficients that are in a vector. It's going to be approximately equal to y. And on the left bottom here we can see, remember, y equals y parallel and y perpendicular. That's just vector addition there. And if I just isolate y parallel, that's y minus y perpendicular. So I can go from this approximation to this equality here. I can say 8 times beta, that's going to equal y parallel. Some linear combination of these 2 column vectors can give me y parallel. But remember, y parallel is just y minus y perpendicular. Now look what happens if I take a transpose of both sides. So I'm going to left multiply this equation here. I'm going to left multiply it by A transpose. And that's going to have a beautiful effect, in as much as if A is not a square matrix, which in our instance it's not going to be, it's going to be a 3 by 2 matrix. If I left multiply it by its transpose, I end up with a square matrix. And that's very nice because if I have a square matrix and those columns are linearly independent, I can take its inverse. And that's going to be very important as well. But let's look what happens. If I take A transpose, left multiply on both sides, that means on the right-hand side I have A transpose Y minus A transpose Y perpendicular. But we just said up here that any column vector in a dot product with Y perpendicular should give me a 0. Now, if I take A transpose, all the column vectors are now row vectors in A transpose. And I'm taking the dot product of each of them with this perpendicular vector, so that all those dot products are going to be 0, 0, 0, so I end up with this 0 vector. And if I add a 0 vector, I'm doing nothing, I might just throw it away. So in the end, we're left just with A transpose Y. So A transpose A times beta equals A transpose Y. So I can solve for this problem, I can attack this problem, and I don't even need the perpendicular component. I don't need the component that's in the plane. I just need Y, and that's what I was given, Y. I don't have to care about those things. It's this magic of taking left multiplying by the transpose. So let's get back to the problem. So we've seen there how we go from this approximation to this equality here if we only consider Y parallel. And here's our full sort of derivation of what's going on. So I've left multiplied here in equation 5 by A transpose on both sides. But I do remember that A transpose times Y perpendicular is just going to give me the 0 vector. So that just falls away. And there we see minus the 0 vector in the second line. And I'd also do some association here on the left-hand side. I'm just looking at A transpose A. And now we've said that if just A has linearly independent column vectors, and in our instance it's going to be because I have a vector of x and then a vector of x squared. That's not linear. One is not a linear combination of the other. One is a square of each element of the other. So that's definitely not a linear combination. So I have A transpose A. Remember, A is going to be for us a non-square matrix. It's going to be 3 by 2 in our instance. If I left multiply that by A transpose, I'm going to end up with a square matrix that has linearly independent columns. And if I do that, I can take its inverse. That inverse will exist. So if I now multiply by the inverse of A transpose A on the left-hand side and on the right-hand side, I have the inverse of a matrix, because A transpose A, that's going to give me a matrix, a result matrix. So the inverse of that times the matrix itself, that just leaves me with the identity matrix. It just falls away. In other words, just remember here the parentheses I'm using at the end, specifically in the last line that has nothing to do with the equation itself there. I'm just explaining what's happening. That we end up here with 6, that we have a solution for this vector beta hat that contains my two unknowns. And that is the least squares, ordinary least squares, this equation that you take matrix A transpose times matrix A, you take its inverse multiplied by the transpose of A multiplied by Y, gives me my two solutions. So if I look at it in this way here on the left-hand side in 7, this is what we have in the moment. My column vector of my x values and then my x squared values. That's my A. That's a 3 by 2 matrix. If I multiply that by beta sub 0 and beta sub 1, it's going to approximately equal that. But I now know if I do the transpose, I'm going to get an exact solution for beta. Of course, it's not an exact as far as my final problem is concerned. That's still going to be approximation. And I just want to show you here that this matrix A, it is linearly independent. These columns are linearly independent. If we take the rank of that matrix, remember the rank is going to give me the number of linearly independent columns inside of a matrix. And I'm using SymPy's matrix function there, uppercase M. I'm constructing my matrix there, and I'm using the rank method there. And if we do that, we see a rank of 2. So this matrix A, really, those two columns are linearly independent, which is great, because that means if we left multiply by its transpose, we're going to get a matrix of which we can take an inverse. Just another way to show you that all 3 columns are linearly independent. So if I create a matrix of the 2 column vectors in A, and I add to that another column vector, which is Y, which I've done here, and I do row reduced, get it to row reduced echelon form, If we were to do that, we end up with the identity matrix. Remember, that does mean is that it's only the 0 vector that is going to give me a solution to the homogeneous problem. In other words, those 3 columns are linearly independent, and we saw that in the little schematic that we have in Google Drawing, that they are all linearly independent. That's what I was trying to show there. Once again, that representation wasn't exactly a representation of this problem, only a schematic to show you what's going on. So just want to remind you how we get an equation for that plane. To get an equation for plane in 3 space through the origin, what we need is a point in the plane. And of course, we've got 2 column vectors here in our plane. So the tip of any of those 2 vectors can be a point for us in our plane. And we need a normal vector, an orthogonal vector to that plane. And how do you get that? Well, we've got these 2 vectors in the plane. And if we take their cross product, we're going to end up with a vector that's perpendicular to them. And that vector is going to be perpendicular to the plane. So that's what we can look at there. And this is how we set it up. And we see the uppercase A, B's, and C's there. Those would be this normal vector's components. And we see the normal vector there. If we take the cross product of our 2 column vectors in A, we see it there. And if we substitute that as 6, negative 3.75, and 1.5 in there, and we take x sub 0, y sub 0, and z sub 0 to be one of the points, one of the tips of our vectors, and we've taken negative 1.52 and negative 1, we solve for that. And of course, the way that this problem is set up, of course, the plane is just going to end up with its coefficients being the components of our normal vector there. And we can just attempt another go at showing that our vector y is not a solution, it's not in the plane. Because if we plug its points into this equation for the plane, the left-hand side and right-hand side of 8 are not equal to each other. That point is not in that plane. So let's use Python and just do these calculations. So I'm going to set up a matrix A. There we go. And there we go. We can see the 2 columns there, 1.52, negative 1. That's the first column. Those are our 3 x coordinates. And I'm just squaring them because we want a quadratic approximation. And I'm just setting up my vector y there. So you've got to see, you don't need to do all these brackets in there. You can just use the reshape method if you want to, setting those values to negative 1, 1. But I've just done them individually just to make sure that this is a column vector. And now we're going to use equation 6. Remember, that is the transpose of a matrix times the matrix. And you take the inverse of that, multiplied by the transpose of that matrix times y. And that's going to give us beta, the vector beta. And of course, it has to have 2 values in it. It's a 2 by 1 matrix, or a 2-element column vector. And we see there. So let's just extract those 2 individually and store them as beta 0 and beta 1. So I'm just using some indexing there just to store those 2 values. And now I want to plot, finally, I want to plot this solution. So what I'm doing here, I'm just creating a bunch of x values, and I'm using the numpy's arrange function there, going from negative 2 to 3 in steps of 0.05, just so that I had plenty little dots. And then what matplotlib is going to do is it's going to make a line from that. And then my solution, remember, which is just a quadratic, I said it's beta sub 0 times x plus beta sub 1 times x squared. So I'm just doing that for all of the values in my array there, so that I have x and y values as little dots. And then, of course, matplotlib is going to create a line from that. And then again with xkcd, what we're going to do is just create this figure. I'm going to put my dots in the figure, and I'm also going to plot this red line, which we can see there, of x and y values, so that we can see both the 3 points that we had and this quadratic approximation. It's not going to go through all those 3 points, and I've explained to you exactly why that would be. It's not in the column space. And there you can see that would be the best approximation that we can find. That, of course, we did not put a y-intercept, so it's going to go through the origin. And there are my 3 points, and it is an approximation. So this, you can see it's starting to curve, so it is going to be a parabola, and it is the best fit to these 3 points. Now, if we bump this up and we make this a cubic, if we try a cubic approximation, we're actually going to get a cubic solution, as a cubic equation that is going to go through all 3 points. Let me show you. Once again, if in here in equation 10, if we set up this problem, we're going to have x plus x squared plus x to the power 3. So it's going to be a third order polynomial. So they'll make it a cubic equation, and it's going to solve. But now we have to have 3, beta sub 0, beta sub 1, and beta sub 2. We need 3 coefficients for this problem. So let me just create this matrix. And I'm just going to show you that these things are linearly independent. This column vector x squared, column vector x cubed, just doing the row reduced echelon form of that. Using this is using SymPy. If you don't use SymPy's matrix function there, you won't have this method available to you. It's not a NumPy. And we see the identity matrix there. So those columns are definitely linearly independent. So let's create a NumPy matrix of A. Remember, y is unchanged. And I'm just going to use exactly the same ordinary least squares equation, equation 6 there. So the inverse of A transpose times A transpose times y, and I get a solution. This time it's going to have 3 elements. So 3 by 1 vector there. And then just saving them individually. Again, just creating my x values and y values so that I can plot them. And now finally we plot this whole solution. And you can see with a cubic, of course, it's going to go through all 3 points. If we had 4 points and we wanted to go through all 4 points, of course, we're going to have a 4th order polynomial. And this, might look neat, but it's not always what we want. What we want most of the time is a linear approximation when we do applications, because we don't want to, what we call, overfit the data. Because if we create this, it's going to fit our data, but when we want to use this on unseen data, it might not do so well. So let's do a linear approximation. So this is going to be a bit different. We know a straight line into space. There we have y equals mx plus c. We have it all the way up there. And m is the slope, c is the intercept. And for the slope, we're going to have beta sub 1. And then for the y-intercept, we're going to have beta sub 0. And the way that we set it up here is in equation 11. It's a bit different from what we've seen before. So there's my vector y, 1, 5, negative 2, all those values. Right on the right-hand side, we see the vector of x values, 1.5, 2, negative 1. And we're going to multiply that by the coefficient beta sub 1. But we need this beta sub 0 as well. And what we do to make this vector equation work out, we just put a vector of all 1s, because a scalar times each of these 1s is just going to be that beta sub 0, beta sub 0, beta sub 0. So that I can read them off again. So the 1 is going to be, the first 1 there is going to be approximately equal to beta sub 0 times 1. So it's just beta sub 0 plus 1.5 times beta sub 1. And that's still an approximation, because I want to remind you, I've just used slightly different notation in 12 here, where I've put a hat on the y. That is in applications where we're just going to get this approximate value of y. We're not going to get this value. Just showing you a bit of different notation, but really that's not what this explanation is about. I want you to stick to the original explanation that we had. And now if we want to create a plane, remember it's just the cross product now of these two column vectors, 1, 1, 1, 1.5, 2, and negative 1. If we take its cross product, as we do there, we see that we can create this equation for our plane. And I'm going to, just to show you that what that plane would look like. But then I'm going to create matrix A there now with the 1, 1, 1 as the first column vector, and then we're going to do exactly what we did before. So there's my solution using equation 6, ordinary least squares. I save beta sub 0 and beta sub 1. I just create a bunch of values so that I can plot it, and there is the magic. We can see the linear approximation of our problem. And this is usually an application of what we would go for. We want this linear approximation. It does not fit the data as well. It is just an approximation, but it probably will generalize much better to unseen data when you use this linear regression here as the creation of a model. So there we go, ordinary least squares and how we use it to approximate a model, at least for the points in a plane.